Hi everyone, my name is Yafeng Wang. I'm from the Department of Mechanical Engineering, Texas Tech University. And today I'm going to present one of our recent research regarding the parking occupancy detection. So in today's talk, it concludes 5 parts. The first part is the traditional methods. And in that part, I will introduce some of the traditional way to do the parking management. And after that, I will present some of the challenges or problems in the existing methods. Then I will introduce our proposed portable parking occupancy detection system, and I will start from the system structure, then followed by the car detection algorithms. And in the car detection, we have considered some real-life disturbances. And after that, since we propose a portable system, there must be a trade-off between the camera moving speed and the image quality. And regarding that, we're going to investigate that problem and finally conclude optimal speed. And later, I'm going to show some of our experimental cases, followed by the conclusion of the whole study. So the traditional method for the parking management is straightforward. For example, we can constructing parking gate, and there's much easier way is that we can using sensor-based system where we can just install a laser sensor or a car detector at the entrance of the parking lot. However, that's not always the case because such a system, even the sensor-based system, is very challenging to implement on the parking scenario like the special event parking. The special event here means sport occasions or music festivals like a football game, for example. So the special event parking management is always challenging. That was because the special event parking is always combined or include complex parking scenarios. For example, temporary parking and on-street parking. So for the temporary parking, the cars are randomly enter the parking area. And that means there's no clear entrance of the parking lot. And if you want to implement or install a sensor, you can't find the right position. The same situation happens on the on-street parking, and where if you want to use sensors, it's nearly impossible to cover every single street. The second challenge is that the parking location for special event are always distributed. For example, this figure is the parking instruction map for the football game in the university I'm studying. As you can see on the map, all the yellow area are reserved to fans. So in this case, if you want to implement sensor-based system, it's gonna be labor intensive and time consuming. Also, the maintenance cost gonna be high. So in this case, a portable system might be a good solution. For example, a quadrotor. We can command the quadrotor to fly over the campus and take the image of the parking lot. Then we can do image processing and finally get the parking information. And this is what we're gonna do in this paper using quadrotors. However, even though we're using the quadrotors, there's still some challenges. First, the whole system should be flying totally outdoor, working with outdoor parking lot. And for outdoor parking lot, it's very normal there will be trees. So what if the trees are blocking the car? The second question is about the human factors. Because for the special occasions like music festival or sports occasions, it's very normal that family get together, they talk to each other, they will gather their stuff from their trunk or they'll open their door. So in that situation, the image of the car is not a normal image of the car. So what are we gonna do with that? The fourth challenge is that since we are using the quadrotor, there will be a trade-off between the quadrotor flying speed and image quality. It is clear that if we speed up, we fly with a higher speed, we're gonna get a better efficiency. However, if we fly too fast, the image quality will going down, which might lead to a detection failure. So the question here is that, how do we determine the optimal speed? Now I'm going to introduce our proposed portable parking occupancy detection system, and I will start from the system structure. So system structures start from here. The parking lot images will be acquired by the Quadrotor, then transferred to the ground station computer, where the image is going to be processed and the occupancy information will be generated and sent out to the driver through mobile devices. So on the right side is the example of our mobile device interface, and it shows that the parking locate at this location has a vacancy of 10. So this kind of information is very important, especially for this kind of scenario, because the driver on the road, is very important for them to know which parking lot they want to go and how many vacancies that they have. Then I will talk about our car detection algorithms, where we have considered some real-life disturbances. For the car detection, we have adopted CNN-based object detection method. While in the training data, we have considered some realistic factors, or say, real-life disturbances. For the first figure, that's a car is blocked by the trees. For the second figure, a pedestrian is passing by. For the third figure, a driver is coming out and checking their trunk. And the fourth figure shows a car with an open door. After we finish the training, we can get a car detection model that can recognize cars in the presence of real-life disturbances. For example, on the right side, the system can successfully detect a car under trees, where the detected car is marked with a rectangle frame. Then I will talk about the optimal speed selection. For the optimal speed selection, we're going to have two steps. The first step is to generate a dataset that contains the Quadrotor speed and the corresponding image detection condition. The second step is that once we have that dataset, we're going to conducting the classification tree learning to determine the optimized speed, VOPT here. For step 1, we have conducted experiments to generate this table. As you can see, we have commanded the Quadrotor to fly over a parking lot with different speeds, from 1 meter per second to 11 meter per second. And for each specific speed, 5 tests are conducted. And if no detection failure happens, we're going to have to mark that speed as 1. 1 means success. And if all of 5 tests are succeed, the final detection result, YI, will be marked as success and 1 as well. On the other hand, if we fly in with a speed of 10.8 meters per second, a detection failure might happen. And in that case, we will mark the detection result as 0. 0 means failure. Once we have the dataset, we can go ahead and conducting step number 2, the classification tree learning. The tree model in this study is straightforward. It has one root node, and that root node A has one split, leading to 2 leaves. One leaf is success, which means if the velocity of the Quadrotor is smaller or equal to VOPT, the detection is going to be succeed. Otherwise, it's going to be failure. Finally, we have determined that the VOPT equals to 9.8 meters per second. And the VOPT here will be used throughout the experiment. So next, I'm going to show some of our experimental cases. For case 1, we're going to conducting experiments on on-street parking lot. And on that parking lot, it has a total of 18 parking spots. And during experiment, 5 are occupied, which lead to a correct vacancy of 13. So during experiment, we're going to have a pedestrian passing by and partially blocking the vehicle. And also a driver will be coming out and checking his trunk. As you can see of the video, there's a pedestrian passing by and partially blocking the car. And the second, there is a driver coming out and checking their trunk, but our system works well with it. This picture shows the result from the mobile device end. The vacancy information is 13, which is correct. For the experiment case 2, we are considering a parking lot with trees. The parking lot has a total of 18 parking spots and 6 are occupied. The correct vacancy should be 12. During experiment, some of the cars are partially blocked by the trees. Here's the video for case 2. As you can see here, the silver and the black car are partially blocked by the trees, but our system can work well with it. As a result, the driver can get correct information from the mobile devices. In this paper, a portable parking occupancy detection system has been proposed. And in the car detection, we have considered some of the real-life disturbances, such as trees and pedestrians. We also investigate the trade-off between the quadrotor speed and image quality, where we have determined the optimized speed to avoid the detection failure. Finally, experiments have been conducted to test the effectiveness of the proposed system in the presence of trees and pedestrians. That's all for today. Thank you very much.